Hi, my name is Mariam Hosseini from University of California, Irvine. I am presenting the paper Application Characterization for Near Memory Processing, which has been accepted for publish at Parallel Distributed and Network-Based Processing Conference. This has been a joint work between UC Irvine and KTH Royal Institute of Technology with Masume Ebrahimi, Puriya Yaqini, and Nader Bagherzadeh. In this paper, we first redefine a set of NMP-centric performance metrics in order to analyze the efficacy of a given processing unit. Leveraging the proposed metrics, we characterize various sets of applications to assess the suitability of a processing unit in terms of performance and energy efficiency. Specifically, in this work, we motivate the efficiency of NMP subsystems to process memory-intensive applications when 3D NVM technologies are employed. What are the motivations behind this work? End of Dennard scaling and Moore's law are causing computers' performance to reach a plateau. Also, at the same time, we are witnessing another challenge in today's conventional computing systems. In the era of big data with emerging data-intensive applications, an enormous amount of data is being generated across multiple areas such as health sciences, chemistry, physics, and IoT. Processing this huge amount of data results in frequent data movement between the memory subsystem and the processor unit, which has a severe impact on performance and energy efficiency of the whole system. So, alternatives are needed to improve performance and energy efficiency by avoiding data movement overhead as much as possible. Different architectural techniques proposed to tackle latency and energy problem when processing data-intensive applications, starting with PIM or processing in memory. 2 decades ago, several research studies investigated the integration of processing logic in DRAM or the embedded DRAM modules on a single chip. Although it was reported that there was potential for a significant speed up in some classes of applications, there was a limited success on the past PIM projects, and the major reason comes from additional cost, which is related to integrating logic and DRAM module, and also density shortcoming of 2D chips. The next technique is NMP or near memory processing. Recently, 3D integration has emerged as a promising technique in memory systems. This technology integrates multiple memory layers and a single logic layer vertically stacked on the same package using short TSVs, which are used to ship data from memory dice to the logic layer. This memory technology promises significant improvements in performance and power consumption compared to traditional 2D planar memory devices. The focus of this work is on NMP as an architectural technique to improve performance and energy. In this work, we redefine a set of performance metrics with the focus of application characterization on host CPU and 2 different NMP subsystems, 3D DRAM-based NMP and 3D PCM-based NMP, to analyze and suggest the suitability of different processing units for the set of characterized applications. We evaluate our conventional base system using Gen 5 NVMe hybrid simulator. The simulator integrates the full system simulator Gen 5 with NVMe version 2, which is a main memory simulator for emerging NVM technologies. We model the base host processor with 16 alpha cores running at 1 GHz frequency. DRAM memory is modeled with DDR4 memory configuration. For the evaluation, we consider applications from different benchmark suites, Parsec, Parboil, and Rodinia to cover a wide range of application domain. Table in this slide lists the evaluated applications and their domain. A comprehensive characterization is conducted on the various applications. The characterization, temporal locality, operational intensity, read-to-write ratio, and row buffer locality illustrate the key behavior of the applications and helps to suggest the most suitable processing unit for each application. Temporal locality and operational intensity metrics are used to evaluate the amenability of various applications to host CPU processing and near memory processing. Using these two metrics, applications are characterized into CPU bound and memory bound. After characterizing applications into CPU bound and memory bound, read-to-write ratio and row buffer locality are used as NMP-centric metrics to evaluate the amenability of memory-intensive applications to near 3D DRAM processing and near 3D PCM processing. Temporal locality is the measure of how likely a data is to appear again in a sequence of requests after being requested within a time span. We use this metric to characterize how efficiently an application could use cache hierarchies. Applications with significant temporal locality can benefit from host caches. However, applications with a very low or no temporal locality, which are cache-unfriendly applications, waste energy and memory bandwidths. One way to estimate the temporal locality of an application is to analyze how the second-level cache miss rate of a processor changes as we increase the cache capacity. This figure shows the temporal data locality sweeping L2 cache size with fixed cache line of 64 bytes across all the evaluated applications. This slide shows the result of operational intensity for all the evaluated applications, which characterize applications into CPU-bound and memory-bound. Applying the roofline model, we relate the performance and operational intensity of an application to the peak performance of the underlying processor and memory bandwidths. Roofline model shows the peak performance, peak memory bandwidths, and operational intensity all together in a two-dimensional graph, which is shown in the left figure. Based on the constructed roofline graph, the modeled host system has a peak performance of 2.4 gigaflops per second in log 10 scale and peak memory bandwidths of 1.79 gigabytes per second in log 10 scale. For a given application, a point can be found on the x-axis based on its operational intensity. The minimum operational intensity to get the maximum performance is pi over beta, which is 1.34 flops per byte for our host processor, shown in the left figure. As it is illustrated in the right figure, applications with operational intensity greater than or equal to 1.34 flops per byte are CPU bound, and applications with operational intensity less than 1.34 are memory bound. Based on temporal locality and operational intensity metrics, we can conclude that applications with high operational intensity and high temporal locality are CPU bound, which can benefit from host processing power and large cache hierarchies. Applications with low temporal locality and low operational intensity are memory bound that can benefit from NMP systems. Some applications show a mixed behavior of poor or no temporal locality and high operational intensity. For this set of applications, we use memory bandwidth utilization and L2 miss per clue instruction or L2 MPKI metrics to determine their memory intensity. L2 miss per clue instruction determines memory intensity, which denotes the number of DRAM requests per clue instruction. This figure shows memory bandwidth utilization in gigabytes per second and L2 miss per clue instruction for applications with no temporal locality and high operational intensity. A very low memory bandwidth utilization, which is less than 0.02 gigabytes per second, and a very low L2 miss per clue instruction, which is less than point 2, determine that such applications have a negligible memory footprint, which categorize them into CPU-bound or CPU-friendly applications that can be processed efficiently on host CPU. For the second phase of characterization, first we use read-to-write ratio metric to characterize memory-intensive applications into memory read-intensive and memory write-intensive. Then, row buffer locality is used to characterize memory read-intensive applications into applications with high row buffer locality and applications with low row buffer locality. A very high read-to-write ratio indicates that read bandwidth has the major impact on the system performance. So for memory-bound applications with a very high read-to-write ratio, which are memory read-intensive applications, near 3D PCM processing would potentially outperform near 3D DRAM processing because of power saving in the 3D structure and a very low standby power offered by PCM technology. Table here shows the device level comparison of DRAM and PCM technologies, and the right figure shows the result of application characterization based on average read-to-write ratio for memory-intensive applications. Row buffer locality is used as an NMP-centric metric to examine the possibility of processing memory read-intensive applications close to 3D DRAM and 3D PCM. Choosing this metric, we assume a same style buffering and size for row buffer in both DRAM and PCM. The right figure shows row buffer hit and miss rate for all memory-intensive applications. Using row buffer metric, we characterize memory read-intensive applications into groups with high row buffer locality and low row buffer locality. We do this based on the ratio of PCM and DRAM row buffer mislatency, which is shown in the table, and applications row buffer hit to row buffer miss ratio, which is shown in the right figure. Memory read-intensive applications with high row buffer locality are good candidate for near 3D PCM processing, and memory read-intensive applications with low row buffer locality are good candidate for near 3D DRAM processing. This slide provides insights for our work. In order to suggest the most suitable processing unit, host CPU processing or NMP, 3D DRAM NMP, or 3D PCM NMP, we redefined four performance metrics to characterize various sets of applications. The first two metrics, temporal locality and operational intensity, characterize applications into CPU intensive and memory intensive, and the next two metrics, read-to-write ratio and row buffer locality, classify memory-intensive applications into read-intensive and the write-intensive groups. For applications that show a mixed behavior of low or poor temporal locality and high operational intensity, we use another two metrics, memory bandwidth utilization and L2 miss per clue instruction, to evaluate their memory intensity. Finally, based on applications class, we suggest the most suitable processing unit in terms of performance and energy efficiency. The table in this slide summarizes all evaluated applications and their characteristics. Based on the redefined metrics, the best processing unit is suggested for each class of applications. In this table, pi refers to the peak performance of the modeled host processor, which is 2.4 gigaflops per second in like 10 scale. As you can see from this table, applications are classified into three groups: CPU intensive, memory intensive, and mixed applications. The host CPU is the best processing unit for the CPU intensive applications. NMP enabled by 3D DRAM is the best processing unit for the memory write intensive applications. NMP 3D PCM is the best processing units for the memory read intensive applications with high row buffer locality, and the host CPU processing is the best processing option for the mixed applications with the low memory bandwidth utilization and low L2 miss per kilo instruction. Thanks for your attention. If you have any question, please don't hesitate to contact me.